All right, so we're to our second question on our practice exam 2, beam bending. So I'm going to go to our canvas and let's take a peek here. Here we go. Let's go to our canvas page. And let's go to our pages. And then we can go to week 11. And let's find our beam bending, this notebook here. So let's check it out. We'll use this to solve this problem. So we're told it's a ceramic beam, 500 millimeters in length, 7.6 in thickness, 10 in width. So I'm actually going to go ahead and start by plugging that into Mathematica. If it pops up, actually, first I need... Excuse me. Oh. All right, so let's minimize this. So if it's a ceramic beam, then we know it's 300 megapascal, or 300 gigapascals, excuse me. The length is going to be 500 millimeters, so 500 times 10 to the minus 3. Forget about a load, P. My width is going to be 10 millimeters, so 10 times 10 to the minus 3. And the height, or the thickness, is going to be 7.6 times 10 to the minus 3. And it's a rectangular beam. So we have our function. We have a load, which is minus 100 times 10 to the third, applied at L over 2, as we see here. Our boundary conditions are going to be at y equals 0. Basically, our slope is 0, or basically no deflection at 0. Our slope at 0 will also be equal to 0. 0 I'm putting right here at the edge. And then we'll have some metric boundary conditions at the other end at L. So let's go ahead and put L here. Let's go ahead and put L here. And we can start to move through here. So let's go ahead and solve. We'll pull out this value here. That's going to be my solution. I don't even really need to full simplify. So that's our displacement here. And as we expect, it's going down. Good. So identify where the maximum displacement of the beam occurs. So I'm going to actually cheat a little bit and start it at 0.2. So this is going to be our maximum or minimum displacement, and it occurs effectively over here. Good. Makes sense. What is the value? Well, this is the value of the displacement. This is where it occurs in product x in the beam. Where is basically the maximum stress occur? So we can kind of see here, actually it's very nice and symmetric. So let's go ahead and actually we're going to look at the edges here and here. So we're going to find, actually let's find minimum. And it is symmetric, so we can say that this is our bending moment. And if we look at the top of our beam, we see that we are in tension. Now, does this make sense here? So if we look at our beam, it's positive curvature. Yep, so we're in compression on the top, and on the bottom we'd be in, actually, excuse me here. Actually, excuse me, it's going to be minus. So our bending moment here, actually at the bottom, let's go ahead and let's define this here. Actually, it's a little bit complicated because, actually, if we look at our beam here, it's actually a little bit complicated because it's looking like this here. So like our beam kind of looks like this. So we're actually, this kind of makes sense because here, and then a beam looks like this here, and then here and here. So if we look at what's going on here, we should be tension at the top. Let's see if that's the case. Yeah, tension at the top, and then we should be in compression on the bottom because of just the way that beam looks. Excellent. Will the beam yield? Let's see. What information are we given here? Ceramic beam. we're told, let's see, the beam in the problem is the blue curve. So will the beam yield? So our yield strength is about, let's say about like 100 megapascals. So let's look at our stress here. Oh yeah, we are definitely yielding. So it will indeed yield for sure. What will be the critical crash required to fail in the stress state? The surface tension is this. Surface tension means that we can use our stress is equal to square root of 2 gamma E Griffith criteria pi A. So we can say that this is our stress. So I'm just going to call this stress. We want to look at tension because that'll open up the crack effectively. So let's go ahead and solve stress at equal to square root of 2 times 50 times y divided by pi times a. So this would be the stress required. Anything's going to break that. So nanometer crack, that's going to go. It's going to fail quite easily. 3 viscoelastic materials, blue, red, and black. The x-axis is strain rate. Which symbol correlates to storage and loss modules? Which is the most solid, which is the most liquid? So if this is strain rate, and we're increasing in strain rate here, so at high strain rates, we should be solid. So this is going to be all of my open points here, basically open symbols. That's going to be my G prime, my storage modulus. My loss modulus will be here at lower strain rates. I should behave more liquid, so that's G double prime. And so if we're looking at this is where we're liquid, and this is when we're solid. So we're going to observe that this probably has the biggest crossover. So let's see how we can analyze this. So like as we're increasing strain weights, we're still behaving, or low, 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 and then finally we're behaving like a solid, where the solid transition occurs basically at even lower strain rates here. So my most solid is going to be my black. My most viscous or fluid is going to be my, actually, let's see here. Sorry. I'm just going to try to see this crossover point. Well, actually, the crossover would be here. They're very close. So actually, excuse me, my most solid is going to be my red. And then my, it's like almost a tie, and probably a tie between the most fluid of black and blue. But you see where we're going with this analysis. So, excellent. Problem 2 on the exam is done for the practice exam. So let's get to the next problem, which is, yahoo! It's thin wall pressure vessel time. So we'll see you in the next video. Thanks.